So the first question on the UIL exam doesn't have to do with programming at all, which is kind of funny because most other questions do. What the first question deals with is something called, I guess you can think of it as like number bases or bases of numbers. What I mean by that is when we describe numbers, like let's take the number 3,491, we talk about this in terms of base 10. You may have heard that we are in base 10 just because we have 10 fingers. But what does base 10 actually mean? Well, what that means is we can represent this number in terms of tens. So this 3 is in the thousandths place, right? So we can represent this as 3 times 1,000. And then this entire number can be represented by 3 times 1,000 plus 4 times 100 plus 9 times 10 plus 1 times 1. Okay? And the reason why I kind of write it like this is because we can represent this in another way, by using 10 raised to some power. So this is the same as 3 times 10 to the third, because 10 times 10 times 10 is 1,000, plus 4 times 10 squared, plus 4 times 10 to the first, because 10 times any number to the first is just itself, plus, oh, sorry, this is a 9. That's my bad. Plus 1 times 10 to the 0, because any number besides 0 raised to the 0th power is 1. So when we multiply this, or when we add this up together, we'll see that this exact thing is the same thing as 3,491. So the reason why we call it a base is that this number right here is kind of arbitrary. So we chose 10 probably because we have 10 fingers, so we can, like, I don't know, it's just like the first number that kind of comes to mind, maybe to cavemen. But when we are computer scientists and we're slightly more sophisticated than cavemen, besides Monday, we'll see that we don't need 10 to be here. This could be any number. So for example, we could have maybe base 2. So we have 2 to the 4th, 2 to the 3rd, 2 to the 2, 2 to the 1, and 2 to the 0. Now the question is, how do we represent each digit in this new weird spooky system? Well, we can really do it mostly the same way. So what's the largest digit we can come up with in the 10 base system, the one that we're usually messing with? Well, that's 9, because if you go one more than 9, you have 10, which is made up of 2 separate digits. Well, in base 2, the largest you can come up with, even though we know that 2 is a digit, the largest we can come up with is 1. Because really, for any base, the largest digit you can come up with is the base minus 1. So like if we have a base system of 5, the largest digit you can write down is 4. If you have a base system of 7, the largest you can write down is 6. If you try and go down to 7, this is like the same thing as going from 9 to 10. Now it suddenly becomes 2 digits, and the number in the ones place now becomes 0. It kind of resets. So basically, whenever you hear of like 1s and 0s, that's because the computer reads information in terms of binary. You don't really need to know that, by the way. But that just means basically we can represent numbers in terms of only 1s and 0s instead of like 1 through 2 and 3 and 4 and 5 and 6 and 7, 8, and 9. The reason for that is that we can have an on and an off switch rather than like weird probabilities of like how much power is being like out of like hardware. Again, you don't need to know that for UIL, but it's just like a fun fact. So let's say we have the number like maybe 1, 0, 0, 1, 1. A common question we'll see, oh, by the way, when we write this in terms of binary, if we don't want this to be confused with 10,000, oh, sorry, I missed a 0 in here. We don't want this to be confused with 10,011. The way we'd notate this is 10, and then this is called subscript when you write like a tiny letter or number, 2. So this just means that we're in base system 2. So like if we wanted to write this in terms of like base system 5, or if we want to say that this number is in base system 5, we would write 5 here. And it goes for anything. Even 10, you would write it. So if we want to convert this to our base system 10, because right now it's in base system 2, this is a common question we'll see on a UIL test. And the way we do that is we literally just like kind of hear how we took like a digit and multiplied it by like 10 to whatever. It's the same thing with binary. So if we want to convert it to decimal, all we got to do is take the digit and multiply it by like the place it's in. So this is the same as 1 times 2 to the 4th plus 0 times 2 to the 3rd plus 0 times 2 squared plus 1 times 2 to the 1st Sorry, I'm running out of room. We can move over. Time plus 1 times 2 to the 0. So let's think of this. So as you mess with binary more, you'll memorize this. So let's work from here first. So any number besides 0 raised to the 0th power is 1. So this is really 1 times 1 plus 1 times 2 to the first. Well, that's just 1 times 2. Plus 0 times something. Well, that's just 0, so we don't have to worry about it. This is just 0. That's nice. And 1 times 2 to the 4th. Well, let's think about it. So 2 times 2, which is 2 squared, is 4. 2 times 2 times 2 is 2 cubed, which is 8. So 2 times 2 times 2 times 2, you just double 8. So that's 16. This is really for anything. So as long as you go up a power, you just double it. So 2 to the 5th would be, 32. And you just keep doubling. 64, 128, 256. You probably only have to know like 256 for UIL, but they could go larger if they wanted to. And then it would just be like, 512. So let's write this over here. So that's 1 times 16. So this is just 16 plus 2 plus 1, which is equal to 19. So this is a question you could see on like maybe an invitational test and maybe a district test, but this is getting too easy for district really. So the shortcut with binary specifically is everything will either be a 0 or a 1. So another way you can think about it, so if we have the number like 1, 1, 0, 0, 0, all we have to do is really just add the values where there is a 1. Because if there's a 0, it's going to be 0 times like whatever, and 0 times whatever is 0. So like in this case, we just see this is going to be 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, and if we remember, this is 8, and then 2 to the 4 is 16. So this number right here, oh, sorry, I forgot my 2, is equal to 24. Because remember, you just add these two together. And as you may like wonder, like, wow, how did you know which like the values of these so quickly? And that's just because when you mess with binary, you get pretty familiar with just like pretty simple numbers. Okay, a slightly more complicated question is this is something you'd see on district and maybe regional. Is we have a number in binary and we want to convert it to another base. There's different weird, complicated ways you can come up with this, but the way I recommend it is just convert it to base 10 and then convert it to whatever system you have. And we'll learn how to do that shortly. So let's say we have the number, let's pick something easy, 1, 1, 1 in base 2, okay? And we want to convert it to base 5. And you wouldn't see like an open free response question for that. What it would be is like 1, 1, 1 base 2 is which of the following, and maybe you'll have like 231 in base 4 or like 50 in base 10, and then maybe the correct answer in like base whatever, and then like maybe you'll see later there's like something called like hexadecimal, which we'll see with. So the most common you'll see is like 2, 4, 8. It's called like octadecimal, I think. Or base 10, which is called decimal, and hexadecimal. But you could have anything in between because the same logic of like this 2 stuff applies. You just plug in whatever number here. So let's say we want to convert this to base 10. Well, the way we do that is we just add these up. So this is 2 to the 0. I'll write it out. So like 2 to the 0 is just 1. So this is going to be 1 plus, and then this is 1 times 2 to the first, which is just 2 plus, and then this is 1 times 2 squared, which is 4. So this is 7. So this is 7 in base 10. And what is this in... Oh, this is a bad example. I'm sorry. What is this in base 5? Well, I don't know. This is actually a good example. So the way we think about it, so if we have base 10 and we want to convert to another base system, you think of the largest power of the new base you want to convert to, and then you find out what you can multiply that by, and you'd write down that digit, and then you subtract that value, and then just repeat that process. So what I mean by that is let's think of 5. So what are powers of 5? We got 1, then we got 5, because this is 5 to the 0, 5 to the 1, and then this is 25. Well, 7 is between 5 and 25, so we know that that 25 is too large. So we will not have 5 squared. This is not a value. So instead, the largest power we can come up with is 5. So, and remember, this is 5 to the first. So we would represent this as a 1, because if we think about it, this is 1 times 5 to the first. So, and if we go like any more, so like 2 times 5 to the first, this would be equal to 10, which is bigger than 7, and we want to keep being smaller. So, we can only write a 1 here, and this is in the 5 to the first place. And then all we have left is 7 minus 5, which is 2. And if we think about it, all we have left is 5 to the 0, which is equal to 1. And what number times 1 is equal to 2? Well, that's 2. So this is, I don't want to say 12, but it's like 1, 2 in base 5. Okay, so let's give a more complicated example. Let's do like 37 in base 5. Sorry, 37 in base 5. And then let's convert this back to binary. So the way we would do that is, again, we would just take 3 times 5 to the first plus 7 times 5 to the 0. Well, what is this? This is 15 plus, well, this is really just 1, so this would be 7. So this would be 22. Cool. So this is 22 in base 10. So you can see that going from like some base system to 10 is really easy. And it's just more difficult to go from base 10 to some other base. So now we have 22 in base 10, and we want to convert this to binary. So let's just think about the largest base of, or a largest power of 2 that is less than this number. So we got 1, 2, 4, just keep doubling, 8, 16, 32. Well, 32 is larger than 22, so we know that 32 can't be here. So we're going to take 22. So if we think about it, this is 2 to the 0, 2 to the first, 2 to the second, 2 to the third, 2 to the fourth. Okay. So now, let's see. So this would be 1 times 2 to the fourth. So we're going to write that down because that's the digit. So this would be 1. Okay, and then now let's think about it. So we're going to do 22 minus 16, because now we represent that 16 here, and we're left with, what would that be? A 6, sorry, long day. Let's think about it. So the next system, so we're done with 16, the next largest base is 8. Well, 8 is larger than 6, so that's actually not good. So the next we want to, so since we wrote down this 1, for this 8th place, so if we think that 16 is right here, we want to write down a 0 next to it, because this represents the 8th place, and we don't want any value for 8. So the next value is a 4. And 4 is less than 6, so we know that we're going to have some number here besides 0. And we think about it, if we like double 4, so if we do 2 times 4, well, we're just back at 8. And we can't even do 2 because that's equal to the base. So we know that it's a 1. This is 4. So now let's do 6 minus 4, which is equal to 2. And now we think about it, well, this is 2 to the first, which is just 2. So, hey, this is perfect. So this is a 1 in the 2 place. And now all we have left is, well, 2 minus 2, which is equal to 0. So we have nothing left. So there's nothing going to be in the 1 place, so we're going to represent that as a 0. So this is 1, 0, 1, 1, 0, base 2. And that's really it. All the way from invitational to state. This is most of the information you need. So I just recommend you go through those UIL tests, and you start converting it. There's one other thing you need to know, though, and that is how do we represent stuff with bases larger than 10. So for example, base 16, which is called hexadecimal. So if we have something in base 16, how are we going to represent the number 10? Because we can't represent it as 1, 0, because this could mean a 0 in 16. This could be 0 times 16 to the 0, plus 1 times 16 to the first. But that's not what we actually mean. We actually mean the value 10 is going to be in maybe the 1 spot for hexadecimal. So the solution is we use letters. So 10, so like for hexadecimal goes 1, 2, dot, 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 like 8, 9, and then the way we represent 10 is with the letter A. And then 11 is letter B, C, D, let's see, 10, 11, 12, 13, 14, 15. Oh, not G, H. No, sorry, not H, G. Okay, and this is 15. And if you go any larger, well, now you're in the same base, so you can't do that. Cool. So here's our system. So let's say we have the number A, B, C in base and hexadecimal, and we want to convert this to decimal, which is base 10. Well, let's see. So we know that this is C represents 16 to the 0 times C, and let's see. So let's see. So A is 10, B is 11, so C is 12. So that's 12 times 16 to the 0, which is just 12. Okay. And we're going to add that with B. So B is in the 16 to the 1 slot, so that's going to be 16 times 11 plus, and then 16 squared is in the A slot, so that would be 10 times 16 squared. I'm going to be honest, I don't know what 16 squared is. Well, 15 squared is 225, so I'm going to guess 16 squared is maybe like 246? 16 times 16. 256. Oh, duh, because technically 16 is a power of 2. Sorry, a little bit of a side tangent. So 2 to the 4th is 16. So if you're going to square, you're doing 2 to the 4th times 2 to the 4th, and you can just add the exponents. So that's 2 to the 8th, which is equal to 256. I'm sorry, that's really embarrassing. Okay, but that's really it. So this is all you need to know for question 1. Pretty much up through state. One thing I have seen one year is instead of just representing it with numbers, they'll represent it with where we program. So I won't get into how the program necessarily, but it will be like 0, B, and then we'll have some like 1, 0, 0, 1, 1, 1. Okay, this just means that the base that this is expressed in is binary. So you can look up like whenever you encounter a problem like this, like look up like how do you express like different bases in terms of Java. And I think I can look it up right now. Binary in Java. So you can like Google it and then you search maybe like binary literals. Yeah, so you'll see right here like this is how you represent. This is basically like a byte. So this is what the 0 stands for. Yeah. So that's just something to know. But you probably won't encounter something that weird until state. Okay. Yeah, that's it. So it's kind of long, and there's a lot of math, and there isn't this much math for most of your questions. But honestly, for an entire question that you'll see on every exam, this is pretty simple. So that's it.